Sound check. All right, welcome everyone. Today we're going to be talking about Title 24. The new code changes went into effect on January 1st of 2020, although it is Title 24 2019 code. This PowerPoint is going to be a CEU, and I'll cover that on the next couple of slides. But first, I'll give a little bit of background about myself. I've been at Lutron a little over 4 years. I started off in field service, working on commissioning our commercial lighting control systems from Quantum to Vive to some of our standalone options. In 2016, I took over managing quality training and service for the Vive product, which is a simple, scalable wireless lighting control solution. I covered the Western US and Canada during that time. I was involved in a number of Vive projects, from simple standalone applications all the way up through large campus-wide installations. And during that time, I learned a lot about installation, construction, and Title 24. Recently, about a year ago, I moved to the Los Angeles specification sales team, and now I work primarily with engineers and architects, lighting designers, consulting on large commercial projects. So Title 24 is a big part of my life, and it has been for quite some time. In this PowerPoint, it's going to be broken into 2 sections. The first half will mostly talk about the reasons for Title 24. It'll give a little bit of background on energy consumption and explain some of the impetus for this code that we have here in California. And then the second half, which is probably of most interest to everyone, is going to cover some of the specific changes in the new code. To start off, first I'm going to show some slides that talk about the CEU nature of this presentation. So other than my brief introduction, that's going to be the last time that I talk about Lutron or anything manufacturer specific. The rest of this slide deck is going to be generic and only applicable to the code. So with that in mind, first we have the statement saying that I am authorized to provide AIA members with CEU credit, continuing education credit, and I'll leave that slide up there for a moment if you'd like to read it, kind of go through all the information there. And then the next slide says that I'm a registered provider of GBCI approved courses for continuing education. I'll leave this up here for a moment as well. And then finally, this presentation is copyrighted and it's created by Lutron. So with that, let's jump into it. First, we have this big wall of text that violates a lot of the rules of PowerPoint. So I'll just talk through some of the things that are here. Basically, the goal, like I already mentioned, is to cover the changes in the new code, to explain why we have the code at all, and then we'll cover some of the requirements for new construction and some of the requirements for alterations to existing buildings. To kick it off, let's talk about why we have code at all. Big picture, the world is consuming a lot of energy, and we don't expect that to change. At the time of this recording, a lot of people are working from home due to the COVID-19 situation that we have globally. Regardless, I have positive expectations that's going to clear itself up, and we're going to be on track to be using a lot more energy by 2040. So in 20 years, we expect that consumption to go up by almost 50%. That's a lot of energy being consumed. To get a global snapshot, let's take a look at who are the largest consumers. Little geography quiz here. You can see the largest consumer over there in kind of the mid right-hand side of the screen. That would be China, followed by the US in second place in terms of energy consumption. Before you get too proud of yourselves, pat yourself on the back about how we're less than China, do remember that China has an extra billion people. I think they have like 1.3 or 1.4 billion people, something like that. The US is like 0.3. You can see some other large consumers are the usual suspects. You've got Russia, India, also very populous nations, and then going on, you can see Australia and some places in South America. Point is, we're all consuming energy. This is data from 2016. One thing that you can kind of pat yourselves on the back about if you're a Californian is that California, compared to the rest of the United States, has remained relatively flat in terms of our kilowatt hour consumption per person. So while the population has changed since the 60s and 70s, right there just before 1975, you can see that little dip on the screen and where my mouse is. And as you might guess, that little dip and the the subsequent leveling off of energy consumption in California can be attributed directly to the implementation of Title 24 in our state. The rest of the US had largely continued to track up with people consuming more kilowatts per person, and this makes sense. As more resources become available, as we become wealthier overall, we consume more. We know this from the types of things that we buy, the cars that we drive, and the energy that we consume. But California's maintained relatively flat. Not a bad thing necessarily, not a good thing, but it does indicate that the code is having its intended effect. So now we'll take a look at the driving factors for the contribution to that energy consumption. So what this is showing here is the energy consumption back in 2003 compared to the energy consumption in 2012. And one thing you'll notice is in 2003, lighting was the single largest contributor to energy consumption in the US. And part of the reason for that, if you look at 2003, part of the reason for that change to 2012, where it still is a very large, it's in the top 5 there. The big change, as you might guess, from 2003 to 2012 is the advent of LED technology, which has largely supplanted all of the other types of lighting control that are out there. Or excuse me, lighting sources that are out there. It still is up there in the top. One thing that's a little bit interesting about this is we have broken out cooling, ventilation, and heating into, or refrigeration into separate pieces. Usually those are all lumped together as HVAC, but even still, lighting is a major consumer there. I've been asked a couple of times what the other is. The other is building loads such as elevators, escalators, other power consuming things in a building that don't necessarily fall neatly into one of the other categories that we have shown there. So what can we do about it? What can we do to go after the low-hanging fruit that is lighting? And one thing, I'll go back really briefly and say, you'll notice that the consumption on HVAC has actually gone up a little bit from 2003 to 2012. There's not a lot of room. I don't think we are getting more efficient, but some things such as ventilation, although we think of them as something that's required for comfort, and it absolutely is, there's also some safety of life there. You have to evacuate dirty air in a space, bring in clean air, maintain the pressure in a building, in a large building. That ventilation system serves to make sure that you can actually open doors and you don't get pressure across boundaries. So pretty critical piece, where lighting, we actually still have quite a bit more room for improvement. So wasting energy with lighting, most buildings are overlit. They don't take into account the natural light that's coming into the space, and we leave the lights on when they don't need to be on, either after operating hours or during operating hours when the occupants aren't there because they're at lunch or on a break or something like that. One contributing factor for that is that 75% of these buildings that are still standing here in the US were built before 1989. So you have older buildings that may not have the newest technology in them. They may have had something retrofitted in, but a lot of times the control might just be a switch on the wall, or heaven forbid, a breaker panel where you just turn off the whole warehouse. You hope somebody turns it off before you leave for the day. There's this quote here at the bottom that talks about it kind of summarizes the problem. Most buildings don't deliver the right amount of light where and when it is needed, and it's usually designed for that worst case level, usually higher than desired. So I can say, working with engineers, working with lighting designers, you're trying to create quality of light, but you always want to assume worst case. So I'd rather put more foot candles than fewer if I'm faced with that choice. And we'll talk about some of the strategies, some of the ways that we can dial that back and reclaim some of those potential energy savings. First off, we're going to go to the basics. So at a very basic level, when you dim a light, it can reduce the power consumption. What that graph is showing over here on the right-hand side of the screen where my mouse is that as you reduce the input power, the light will go down, and vice versa. As you reduce the light, the required input power to make that light goes down. So it's a largely straight line there, meaning that if I drop my light output down to about 50%, it will also take about 50% of the power to turn that light on. And that holds true regardless of the type of dimming that we're talking about. So although LEDs are more efficient, it's still something where we can save energy by reducing the light output there. So a couple different ways that this can work to save energy. One, we already talked about, reducing the power, reducing the light reduces the power. We can also reduce the operating hours. So if you have lighting control in the space, we could turn the lights off and we don't need those lights to be on. We can reduce the cooling load on the building. So as we reduce that power consumption by the light, a lot of that light power consumption, you have the electrical components that are there that are getting really warm, and those can place a cooling load on the building. So minimizing light output can also minimize the amount of heat generated in the space, and therefore minimize the amount of HVAC required to get that space down to a comfortable temperature. And then another big thing would be to maximize the effective use of sunlight. So that could be using window covering systems that are integrated with the lighting control system to intelligently allow natural daylight during portions of the day and minimize the electric light. And it can be dimming the electric light when you have that natural light present in the space. So a couple different ways to do that. And we'll go into those in a little bit more detail. Before we go too far and we think too much about saving energy, I do want to make a point here about the fact that saving energy isn't the end of the story. We know that at the end of the day, people have to live in these spaces. So just getting enough light for people to come into work and do their job is not necessarily enough. And I like this quote we have here from Kevin Cavshore. Let's see if I can get the slide to go. There we go. Director of the Office of High Performance Federal Green Building. So zero energy buildings that provide zero comfort or zero productivity increases to the occupants are of zero value. So to break that down a little bit, one of the things that I like to talk about is a JLL study that talks about the 330-300 rule. And that rule, basically applied across the United States, is a way of relating different costs of running a building. So at $3 per square foot, one of the most affordable operating costs, and it's $3 a square foot across the United States, so maybe not the case here in California. Energy. Energy accounts for about $3 per square foot on average across the US. The energy costs to heat, cool, illuminate, power a building. The next cost, a factor of 10 or an order above that $3 per square foot. At $30 per square foot, we have our operations and maintenance, our janitorial facilities, paper towels, the things that you don't necessarily think about that make a building run. That overhead is about $30 per square foot, all those behind the scenes things. And then, as you might imagine, but it may not be the most obvious thing, but I think once you think about it, it's there. The most expensive thing in a building are the people, and that's us. And while right now, as I'm recording this, most of us may be working from home due to COVID-19, largely most of the time, the largest expense in a building is the salary of the employees that work in that building. So if energy costs $3 a square foot, operations and maintenance costs $30 a square foot, and then the people are costing $300 per square foot on average, it's pretty important that those people are comfortable and productive. And to put it in perspective, if I could offer you an amazing lighting control system that could save 100% of the energy in your building, that's not possible, but maybe it could. Maybe I could give you some fancy lighting control system, Title 24 endorses it, and it saves 100% of the energy costs in your building. And the only trade-off is that the employees have to get up, I don't know, let's say once an hour and go hit a button on the wall to just keep the system running. They got to check in, let's say. And that's going to make them 1% less productive. It's not a lot. I mean, they're getting up from their desk, they're losing their focus, they're losing their flow, and they're 1% less productive to keep this energy system running. If those employees are 1% less productive, that's a net wash, because that $300 that you're paying per square foot to keep them employed and keep them happy and healthy has now been washed out by that 1% productivity loss just to get some energy savings. So something to think about as we're thinking about code. So with that little soapbox out of the way, let's move into some strategies that we can employ to save lighting, but also increase occupant comfort. So some of the more obvious ones, scheduling, I've already kind of mentioned this a little bit. We can turn off the lights automatically or dim them at certain times of the day based on how much natural light we have available. We can use occupancy and vacancy sensors to automatically turn lights off when people aren't in the space. We can have multi-level lighting or dimming, basically give users more than one option for their lights. Chances are, if you have the option to reduce your light in your space, you probably will, especially if you have LEDs in the space that are really bright. And then daylight harvesting, taking in that natural light that's coming from outside and automatically adjusting the electric light in the space based on the amount of light that's coming in. Some of the less obvious strategies are these here. So I'll talk first about high-end trim and tuning. The concept here would be that when I high-end trim a fixture, I set the absolute maximum that that fixture can go to from a user standpoint. So I basically set the new 100%. And this has a couple of neat benefits. There's a couple of reasons why you might do this. One is simply occupant comfort. If you've been through an LED retrofit recently, an LED is really bright, and as we mentioned before, a lot of spaces are over illuminated because they're over designed, and just tuning it down can make the occupant more comfortable. If you don't need 60 foot candles at the surface, you really only need 40. Well, right off the bat, we can trim down by 33% and get the 40 foot candles that we actually need in the space while saving about 33% of our energy usage. So that's pretty neat. The other thing that's less obvious that you can do when you do high-end trim and tuning is you can extend the life of the fixture, the useful life of the fixture, and that happens in kind of a two-part way. The first part is fairly obvious. It is if you don't operate the fixture at maximum, it's probably going to last longer. That has broad applicability to many things in your life. If you have a wonderful, reliable Toyota Camry, let's say, and you drive that thing around at 140 miles an hour or however fast they can go. I'm not sure, I'm not a car guy, but you drive that car around at 140 miles an hour, I'd be willing to bet that that car is not going to last nearly as long as a car that is driven at the speed limit and reasonably taken care of. So right there, you can imagine you can extend the life, just not by running it at maximum. The reason for that is you have heat transient. So every time you heat up a fixture and it cools back down, it has a little bit of a warping effect. So if you've ever put a cookie sheet in the oven and taken it straight out and put it on the counter and noticed that as it cools, it can kind of raise up on the corners, the same type of thing can happen to the electrical substrates for those LED components as they come away from the substrate, and ultimately you'll start to have light engine failures. The other thing that we can get by doing a high-end trim or tuning a fixture down is we can extend the useful life of the fixture, because as time goes on, everything tends to degrade, and that LEDs are no exception. So after 5 or 10 or 30 years, the LED light output is not going to be the same as it was for the same input power, because the fixture is just not as efficient as it was. So if we go back to my example a couple of moments ago with a fixture that can provide 60 foot candles, but we only need 40 foot candles, if I reduce that fixture, if I set a high-end trim of 66% or 67%, taking 33% off the top, in 10 years, when that fixture is now providing 35 foot candles, let's say, I can raise the high-end trim up to 75 or something like that and get the same foot candle output. So the fixture is not as efficient, but I'm extending that useful life because I have that buffer. So I spent a long time talking about high-end trim and tuning, but it is really a neat feature of having a control system in the space, and it can lead to occupant comfort and energy savings. The next one down, we already kind of mentioned personal light control, giving users in the space the ability to change their light as they need. The ability to control window shades, so allowing natural light into the space. One thing that's a little bit interesting about shades is that having shades can actually improve the view outside into the environment. And I think most people know this a little bit intuitively, even if you don't think of it with a window shade or with a window covering. When you wear sunglasses, you're taking advantage of that same feature. You have beautiful, bright, sunshiny California. You put sunglasses on in order to see better because it blocks out some of that glare. So properly designed window shades can have the same effect. On a nice sunshiny day where the sun is coming straight through the window like we have here, where my mouse is, pretty difficult to see outside. If I drop a window shade down, let's say something that has a black interior and a white exterior, I can actually get a much better view. The white on the outside will reflect light away from the building, and also it happens to help reduce that solar heat gain and minimize the glare. And then the black on the inside has the same effect as putting on a pair of sunglasses, where you're actually able to see out and get a better view. The last two, it doesn't really matter whether you like them or not, and they are some of the changes that have occurred recently in California. Demand response specifically, I'll spend quite a bit of time on in the second half of this presentation. And then plug load control, everyone's favorite, hasn't gone away. You still have to do it on new construction projects. So we'll talk about that a little bit. So now that we've spent quite a bit of time talking about these lighting control strategies, we're going to apply them to an example building that's consuming a lot of power. Take a look at this graph. We can see, hopefully, right off the bat what some of the problems are. The lights are on from 12 midnight to 12 midnight. So we're not off to a great start. We're consuming 8.76 kilowatts per square foot annually, because we're using, let's say, 1 watt per square foot in this building. So not great. Some of the strategies we can start to apply right off the bat. Let's turn off the lights when no one's there. So we could just apply scheduling. We could add a time clock to this system and maybe keep the lights off from 12 midnight until 8 a.m. and then maybe turn them off again at 8 p.m. until 12 midnight, something like that. Next strategy that we could apply would be to add some occupancy sensing here. So now we're getting a little bit more intelligent. The building maybe goes mostly unoccupied around noon because that's lunchtime, and then maybe people take a small break in the afternoon. So by adding occupancy sensors, the space can dynamically react to the people present and turn the lights off automatically when no one's there. Next thing we can add in is that tuning. So as we start to tune the fixtures down, we can get even lower. And as you'll notice, our annual energy consumption, as we've applied these strategies, right off the bat, we dropped about a third off of it. Then we dropped more than half by adding occupancy sensing. Then we're dropping down to almost 1/3 of the original, a little over 1/3 of the original by adding tuning. And then finally, if we add in daylighting, we can get down to less than 1/4 of our original annual energy consumption. And you might guess why the curve has this shape here. At 12 noon, the sun is at the highest in the sky. Usually it's providing the most light. So therefore, we'd have the minimal requirements for electric light at that time. At the beginning of the day and at the end of the day, you're probably going to have more requirements for electric light. So that's why it has that shape. So you can see here how applying a couple of simple strategies can get you some pretty major energy savings in a building. Taking a look at another graph, just comparing some codes here. So ASHRAE 90.1 is kind of the baseline energy standard for the country, and we're adding in those same control strategies we just saw on some of the previous slides. One thing that you'll notice is obviously the lighting control is, or the lighting power consumption is being reduced by adding these strategies. But one thing that also is happening is air conditioning loads, as we apply more and more strategies, are also actually going down, and plug loads are also going down. And that's because we get some synergistic effects from taking, let's say, an occupancy sensor and allowing the occupancy sensor to communicate to the HVAC system, or having daylighting with some natural shades reducing our heat load on the building, maybe blocking out some of that solar heat gain. So some ways that the strategies can work together to reduce that overall consumption. And one rule of thumb that I'd like to share, I've heard a couple of different numbers, but the one that I'm most familiar with is that approximately for every 3 watts, I've heard 4 as well, but 3 to 4 watts of lighting saved, you save about 1 watt in HVAC power. So pretty significant. All right. We're on to the second half now. This is the part that I would imagine most people are most interested in. These are the changes that come with the code in Title 24, 2019, which went into effect on January 1st. This affects all newly constructed building alterations, and it has interior and exterior requirements. And this little bullet at the end, it says Title 24 might be the strictest code in the country. I'll say that Title 24 is probably the strictest code that is enacted statewide. We're also pretty fortunate to be in California where we have one code for the entire state. A couple of states are a mix and match of different versions of the code, different codes and different versions of the code. So in Hawaii, they might have IACC 2015 in some places, but then IACC 2006 in other places. So we are a little bit fortunate at least to have unified code throughout the state. This slide here is a quick overview of what has changed, and you'll note this kind of blue color refers to anything that you see on the other slides are going to have that same blue color, calling attention to what has changed. So there's going to be a mix in this presentation of mentioning changes, and then also I'm going to do a little bit of a refresher on the types of things that are required by code. So on the refresher note, we still are required to do manual controls in most spaces. There are a couple of exceptions. Typically, those exceptions are going to be in common areas, so lobbies or corridors, and usually the exception is that you have to have the control either in an accessible adjacent space or it has to be enunciated. An enunciated control means that the control has some sort of status indication that shows what the lights are currently doing in the space. So a unlabeled on-off switch in a janitor's closet is not necessarily an enunciated control because you can't tell from the closet what that light is controlling and what the status of, or what that switch is controlling, what the status of those lights are. The multi-level lighting controls are also required in most spaces. There are a few exceptions, and the new exception there I've got highlighted in that blue color would be healthcare facilities. On that note, healthcare facilities are largely exempt from all of Title 24 now, and I've got some definitions for healthcare facilities. Actually, I'll flip back. Healthcare facilities include all kinds of things. So exam treatment rooms, imaging rooms, medical supply rooms, operating rooms, nurses stations. So basically anything that could be considered a healthcare facility is only required to follow the most basic power distribution requirements from Title 24. So multi-level lighting is required in most spaces. And it says here continuous dimming or multiple steps. We're going to get to another table here in a moment. Generally speaking, if it's an LED, it requires continuous dimming. Also, just do continuous dimming. It's 2020. It's kind of a standard option on most fixtures to provide that. So I'd say go ahead and do it. On that note, we'll move forward to the table that shows the requirements. And as you can see here, for line voltage sockets, for LEDs, and even for fluorescents, they mostly require continuous dimming. There are a couple of places that allow for stepped dimming. I'm just going to ask, please don't do stepped dimming. It's kind of a pain from a control standpoint, and it's not a great user experience. So I would say continuous dimming is probably the right way to go. Shut-off controls, again, we have to do shut-off controls, so turning off lights after hours, and the only exception I've got highlighted here in blue, again, is that healthcare facilities. Shut-off controls can be accomplished a couple of different ways. You can use a time clock to shut the lights off, basically automatically turn everything off, and if you do that, it might not be the best experience for the occupants in the space. So there's some strategies that have been implemented over the years to try and let the occupants know. Some of you may have seen blink warn, where the lights flash at you a couple of times, like last call, and you have to go over and maybe hit a switch, and then the lights stay on for a little while longer, and then they flash at you again. You got to go hit the button again. If you ever experienced that, that's because of the requirement that the lights cannot be on for greater than 2 hours during that after hours time frame for a building. A better way to do it, in my opinion, is to add occupancy sensors. It meets the requirement of the code, and it has the benefit of being able to detect whether a person is in the space. So if you've ever experienced that after hours blink warn situation where you have to go up and hit a button, what's actually happening there is the lighting control system is attempting to use programming to determine whether or not a person is in the space. So it flashes the lights, the person gets up and presses a button, and that lets the lighting control system know that someone is still there. That's a pretty complicated way to do something like detecting a person when you have devices that are available to do that. They're purpose-built for it, like an occupancy sensor, which is actually designed to do just that. There are some exceptions for shut-off controls, whether it's occupancy or time clock. If you have buildings that are 24-hour operation, then that would be an exception. Electrical equipment rooms, emergency lighting, and then buildings that have, you can have up to 0.1 watts per square foot of continuously illuminated space for security or emergency egress. So it's acceptable to have some lights that are continuously on, but it has to specifically be for security or emergency egress. This is different than emergency lighting in general. Typically, your emergency lights have to be controlled along with your normal lights. So a room with, let's say, 50 2x4s, like a big open office, you could designate a few of those lights to always be on at some low level, but it can't be more than 0.1 watts per square foot. So I have seen a couple of times where people have tried to get away with saying that, oh, I have all of these lights, they're emergency lights, they're there for emergency egress, but if you go over that 0.1 watt per square foot, you have to control the rest of the lights. So something to be mindful of. Spend a little bit of time talking about occupancy sensors. Those are required in a lot of spaces, open offices, or excuse me, office spaces up to 250 square feet, multi-purpose rooms, so just basically a catch-all there of up to 1,000 square feet, classrooms and conference rooms. And at the end of this slide deck, I'm going to show a couple of resources to help you know when you need occupancy sensors and when you can use time clocks. So that's still there in the code, very much so. Still required to have shut-off controls in corridors. So these spaces allow for full off or partial off, and that would be stairwells, corridors, warehouse aisles, library stacks. And one of the neat things, depending on the type of control system that you implement, is it doesn't have to be one or the other. Maybe you're running a hotel, and in the corridors during the day, you want the lights to go completely off because you have nice natural light coming in through our windows at the end of the corridors. But at night, you don't want one of your guests to walk out into a dark hallway. So you want the occupancy sensor to drop the lights down to 50% when it goes unoccupied, but not go completely off. If you have a system that has a time clock that's capable of interacting with the light or with the occupancy sensors, you can create a dynamic effect where you have a sensor that can behave in multiple ways depending on the time of day or depending on other inputs. Continuing on, for partial off occupancy sensors, the space has to reduce by at least 50% when they're unoccupied. So that would be corridors, like I already mentioned, in hotels. So when you do that partial off, it has to be at least 50%. You can do more if you'd like to. You could drop down to 20, but it has to be at least 50. We also need shut-off controls in parking garages, parking areas, loading areas. One thing that I'd like to point out here is you have to have at least one control step between 20 and 50%. So A/B switching is not necessarily going to be acceptable because you have to have a step in between 20 and 50%. And then moving down to that next bullet, another reason why A/B switching is probably not acceptable is that you can't have more than 500 watts controlled together on a single zone. So for a pretty big, well-lit parking lot, you're talking about only a few fixtures grouped together. And then also all of the controls have to be capable of automatically turning the lighting full on and being activated from any path of egress. So some important new requirements there. Some are new, some are standard, but definitely it's something to be mindful of. Last note on automatic shutoff controls. This is nothing major. Basically, we've just brought guest rooms in hospitality applications into line with the rest of the commercial code. They're now 20 minutes, and that's a code change. It used to be 30 minutes. It's 20 now, which is nice because it's consistent with the rest of the commercial code. The exception is one high efficacy luminaire that's within 6 feet of the door. So you can have a light by the door that is not automatic shut off. Moving on to automatic daylighting controls, this hasn't changed a whole lot except for we've clarified some of the language on side lit daylight areas and some of that skylight fenestration. And the requirement is that you have to have dimming or at least some control steps from that multi-control table in response to daylight. This is going to be one again where I'm going to say the experience is certainly better if you have continuous dimming. The exceptions here would be a room where the total lighting power in the primary zone is less than 120 watts, or if you have a room with very little glazing. So if you have something like those basement windows where it's, you know, a 1 foot rectangle at the top of the room, 1 foot by 4 foot, you're under that 24 square feet requirement. You don't have to have automatic daylighting control in that space. On the topic of primary and secondary daylighting zones, we've got a little table here to kind of explain what that is. So for a typical window, the primary daylighting zone is going to be the effective window height, which is sometimes referred to as the head height. So for this graphic up here where the sun is coming through the window, if this head height is at 8 feet, that head height would be laid out into the space, and that would be your primary daylighting zone. And then a second head height, another 8 feet would be your secondary daylighting zone there. For skylights, this is where I was mentioning they've clarified the language in the code a little bit, but it is going to be 0.7 times the effective height of the window. So the height of the window there around the skylight is your primary daylighting zone. All right, on to the, I would say probably one of the more challenging changes here in the code, demand responsive controls. So I'll spend a little bit of time talking about this. The code has required demand response for a long time. Sometimes it's called ADR, DR, demand response, load shed, automatic load shed, all of those things. And up until this version of the code, it hasn't been specifically defined what is going to be the protocol that triggers the action in the building. So taking a step backwards and talking a little bit about what demand response is, it's this concept that in response to a demand, typically from the utility company, a building can reduce its power consumption. And this stems from some of the rolling blackouts and brownouts. If you've been in California for a while, you might remember some of the energy issues that we had about a decade ago, maybe over a decade ago. This is an attempt to combat that, where basically the utility can tell a building, hey, we're experiencing a period of high demand. We want you to reduce your power consumption. And that power consumption needs to be reduced by at least 15% of the total rated load in the building, or the installed lighting power in the building. It can be more, but it has to be at least 15%. And now in 2020, they have specifically said that demand responsive controls have to be via OpenADR 2.0A or 2.0B, and they have to be able to, or they have to be able to respond to an OpenADR 2.0B signal. So that's a little bit different than it ever has been before. Before, they just said you have to be capable of receiving a signal, and it wasn't defined. So you would have lighting control systems that used a contact closure, or maybe they used a backnet signal from the building management system, or maybe it was activated through a button press in the GUI. A lot of different ways that it could have been done, but now they've gone all in on OpenADR. Personal note here, this is a little bit like if the state of California told all cell phone manufacturers they have to include wireless controls in their devices. Well, there's a lot of wireless control out there. They might include Wi-Fi in their cell phone, they might include Bluetooth, they might include near field communication, they might include LTE, what have you. If California then came out and said, actually, you have to include Zigbee, and it's got to be Zigbee, that's the wireless lighting control that or that's the wireless control you have to have in your cell phone. That's kind of what happened here. Is the state has actually decided that a particular protocol be implemented. The easiest way to tell if your lighting control system is OpenADR compliant is to go to the OpenADR Alliance website. They are a for-profit organization. I'm pretty impressed that they got their protocol written into the code. They There is a requirement you have to basically get on board and get listed on the website. So kudos to them for getting that written in there. The code itself does not require that a manufacturer be listed on the OpenADR website to be certified. However, the acceptance testing forms, which I'll talk about acceptance testing here in a little bit, have a spot for the acceptance tester to verify. So basically, if you're going to use a lighting control system, you better check that the manufacturer is OpenADR compliant. Unless your building is less than 10,000 square feet, you also don't have to have it in any spaces that are less than 0.5 watts per square foot, or the kind of catch-all exception, if the lighting could not be reduced because it would create a safety issue, you don't have to have demand response there. Moving on to some outdoor lighting controls. The idea here, again, is we want to eliminate wasted energy, just now we're outside. The requirements for outdoor lighting controls now require that they automatically shut off when daylight is available. They have to have a night setback where the lights are reduced by at least 50, but up to 90% by scheduling or by an occupancy sensor. And then for motion controls, they're required on any poles or wall-mounted fixtures that are under 24 feet. And so it gets even a little bit more strict. And it says that you have to control them with sensors and reduce the lighting power by 50 to 90% and turn them off or dimmed within 15 minutes of vacancy. So you actually have to have a sensor on those shorter poles, and you can't have more than 1,500 watts controlled by a single sensor. So parking garages, it was 500 watts. It's a little bit less strict here. It's 1,500 watts, but again, they don't want all of the lights controlled by a single sensor. And then for scheduled controls, there have to be at least 2 nighttime setting levels, and the override to on during dim or off states is permitted for no more than 2 hours, similar to the inside of the building. So if you override the lights, they can't stay on. Again, the easy way to accomplish that is just to use an occupancy sensor. So if someone walks by, the lights will go on. When they leave, the lights will go back off, 15 or 20 minutes later, something like that. We'll look here at the power adjustment factors that are available. I mentioned before that there's been some changes to that clear story fenestration, horizontal slats, and also light shelves. The power factors on those have changed. So to give an example there, a power factor of 0.1 would mean that 10% of the watts of lighting power that are controlled with continuous daylight dimming plus off can be used as additional lighting power somewhere else in the building. So that's something you can take advantage of there. All right. This hasn't changed, automatic receptacle control shutoff. This is still a requirement. I just want to talk about a couple things briefly here. One thing is I've heard a number of people say that receptacle control is required for 50% of the receptacles in the space. That will definitely meet the code, but the only code that I'm aware of that requires 50% is guest rooms in hospitality spaces. Everywhere else, it's just one controlled receptacle within 6 feet of an uncontrolled receptacle. So if you have a wall that is, let's say, 18 feet long, and you're going to put a receptacle every 6 feet. So you'd start at one corner, you go over 6 feet, you have a receptacle, and then you start at the other corner, you go over 6 feet, and you have a receptacle. If you put a single controlled outlet in the middle of that wall that's within 6 feet of those other two, you are now meeting the code because you can't go more than 6 feet without finding a controlled receptacle. So we're good there. And it doesn't have to be the whole thing, it can just be the one. Other code requirement is it definitely needs to be marked. It has to say controlled and show an indication on the receptacle that differentiates it from the uncontrolled ones. There's this note here. I think this is kind of obvious, but clearly you can't plug a power strip into that controlled receptacle and have it turn that off. All right, lighting control acceptance testing. We're getting down to the end here. This is still required. You have to have your CoolCat, your Cal CTP certified lighting control acceptance tester to come in and verify that you're meeting the code requirement. And specifically, I'm sure in this new code cycle, they're going to be looking to ensure that you have the demand responsive lighting controls that are compliant with OpenADR, either 2.0A or 2.0B. And the way that they're going to do that is looking at that OpenADR website. There have been a couple of changes to the luminaire alteration requirements. Just leave this up here for a moment. We can dig into this a little bit more, and when we email this PowerPoint out, it'll have all the speaker notes that give some clarification here. There are a couple of exceptions. For instance, I think exception number 1 would be if you're altering portable luminaires or luminaires that are affixed to movable partitions. Those can be an exception. But these are the new requirements for alterations, and it shows here that you basically have to have a lot of the same controls in an alteration under the new code. So for some more information, you can go to the California website. You can use this PowerPoint. Again, the speaker notes have a lot of good information in there. But the energy.ca.gov/title24 has got some great info. And then as this is the end of the CEU presentation, I'll also go ahead and go here to the lutron.com/energy codes website. So I'll leave that up for a moment and go to lutron.com/energy codes. There it is. So on this website, you can see here that I've got a couple of cool reference guides. So one of those, whoops, this full screen. One of those is an entire application guide that's available as a PDF. The one that I like quite a bit is this quick reference guide. This quick reference guide, if it loads, there we go, is a great way to quickly identify what's going to be required for a space. So you can see here it shows the space type. Up here we have the key that shows us the type of construction that's going on. And then that symbol would indicate what we need. So if I'm doing an open office that's greater than 250 square feet and I'm doing new construction, I can see that I'm going to need multi-level lighting control. I can see that I'm going to need occupancy sensing, full on, full off, daylight responsive control, receptacle control, and demand response for a new construction project. That same project would not require receptacle control if it were a retrofit, as a for instance. So some cool indications there, a cool quick reference guide. And then here on the second slide, you can see we actually reference the specific portions of the code. And there's some quick notes here on daylighting zone requirements. The other one that I would like to show, I can close out of this, is this poster. So this is a handy reference poster, also available to be printed, which helps guide you through the code. So some great resources there. And if you're in another state, you can see this defaulted to California when I went to that website. But if you're in a different location, we have all the states in the US, and then I think we also have some municipalities as well. So if I put in New York, I can see that I can look at the state code for New York, but I can also check out the city metro code for New York as well. So great resources there. Okay, so with that, I'm gonna go ahead and end this presentation. Appreciate your attention. Thanks for joining me virtually. Have a great rest of your day. Stay safe and be healthy. And if you have any questions, you can absolutely reach out to someone at Lutron or reach out to whoever at Western sent you this presentation. And thank you very much for your time.